arc length and area of a sector. So let's consider the circumference of the circle is 2 pi r. Now we're just talking about a sector. So let's say the arc length of this sector is L, and the angle in the middle of the sector is theta. If theta is in degrees, then the arc length is going to be theta divided by 360. That's the fraction we have. We've got theta out of a full 360 multiplied by the whole circumference. That simplifies to, now this is the version you would actually use in calculation, but we could simplify it to this, so cancelling the 2 and the 360, and then rearrange. We could get pi over 180 here. And that's the conversion factor from degrees into radians. So for theta in radians, what we'll do is we'll cancel out of this the pi and the 180, and we just get L is equal to r theta. So if theta is in radians, the arc length here is just going to be the radius multiplied by the angle. But remember, that is with theta in radians. You need to use this if theta is in degrees. Now let's consider the area. So the area of a whole circle is pi times the radius squared. We're just interested in a sector here with the angle theta at the middle. So the sector is going to be theta out of a full 360. If theta is in degrees, the area of the sector is going to be theta over 360, that's the fraction we have, multiplied by the area of the whole circle. We can rearrange that to this. So what I've done is I've split the 360 into 180 times 2 and just moved the pi over here. Now, since pi over 180 is the conversion factor from degrees into radians, if theta is in radians, what we do is we've just taken this factor of pi over 180 out, and we get A is a half r squared theta. Now what you notice with both the arc length and the area is that the formula is actually simpler if we're in radians, and that's because radians have this intrinsic link to circles and degrees are just some arbitrary unit.